Hey folks, welcome to this episode on molecular total and net ionic equations. So we do have three equations that chemists use to describe single and double displacement reactions. They all are a little bit different, but they're all related to each other. So when we look at these three different equations, here we can see an example here, our molecular, our total, and our net ionic. Our molecular equation really shows all the compounds and elements as they are. They show the states, they show their balanced coefficients, etc. So this is our balanced chemical equation. We could just call it a molecular equation in this case. When we dissolve ionic compounds that are soluble in water and they become aqueous, in water what they actually do is they don't exist together like this. They actually split up into their separate ions. Now here when we see NO3, we have two NO3, so that actually becomes a coefficient. It just says we have two NO3s. But all these soluble ionic compounds become aqueous, and we split them up into their individual ions. However, you'll notice that PbI2 stays the same; it stays intact, and that's because it's a solid. It's insoluble in water, and so in this case, it doesn't break up into its ions. So it's kind of repeated to the same way. It doesn't actually break up. Again, potassium nitrate split up into ions because it's soluble. So this is a total ionic equation, and it shows all the ions, all the soluble things split up into ions, and all the insoluble things, gases and solids, for example, and liquids, as these compounds together. Now what you'll notice is that there are things that exist on both sides. For example, the lead and the iodine, or the iodide in this case, actually form the lead-2 iodide. But the potassium and the nitrate actually exist on both sides. They haven't done anything. So they're called spectator ions, and we can actually cross these out on both sides and just rewrite what's actually important to the reaction. These things don't actually participate in the reaction. That's why they're called spectator ions. So again, molecular equations, they show the full formulas of all the substances involved. So in this case, we have our aqueous substances, our hydrochloric acid, sodium hydroxide. We create aqueous sodium chloride, and then we create a water. In this case, they're all the compounds there, and if we want to split these up to show all the ions in solution, remember that we have to look at the state. Okay, aqueous things will split up. They'll split up into their separate ions, in this case the H and the Cl minus, the Na plus and the OH minus, the Na plus and the Cl minus, okay, plus, minus. But when we look at liquid or gas or solid, this is a molecular compound. This is not going to split up in water, at least for our purposes right now. So when we do split it up, we get into our total ionic equations. So it's all the dissolved ions, and you can see that we've all split it up. We kept the states with them, the aqueous, 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 and the liquid, the one that we didn't split up. As you can see, the Cl minus and the Na plus exist on both sides. So as you guessed it, we're going to cross these out. And just write what's actually important to the reaction. And what I mean by what's important to the reaction is what is being formed and what is causing its formation. So here we have H2O. The H2O is being formed from the H plus and the OH minus. So those things are important to the production of our water, which is what the reaction is all about in this case. So like we said, notice that the Na plus and the Cl minus exist on both sides. They just spectate the reaction. So they're not actually involved in the formation of what we're focusing on here. And again, that state change that we got in this shows us that this is the key thing in the reaction. So only this and this are really important in creating this. These are just found on both sides. They're just spectating the reaction. So we call them spectator ions, and we cross them out. They're basically just obscuring what is really happening. That hydrogen is reacting with the hydroxide to create the water, and because they're just kind of obscuring our view, we want to get rid of them and really focus on what's important. So when we cross out our spectator ions, we write our net ionic formula. So here's our total ionic formula. It shows us all the ionic species. We saw that these are on both sides, the Cl and the Na plus. We call them our spectator ions. We cross them out, and what we get is our net ionic formula. So this is a really focused formula of what is happening in all this mumbo jumbo of ions. So when it comes to writing net ionic equations, if we're given the reactants in the word form or in the chemical form, we want to switch the products by switching the names, or in the case of formulas, the actual symbols. The best thing to do is always check the solubility of the products first. If you see that they're all aqueous, and it's not one of the exceptions that we spoke about in the carbonic acid, the sulfurous acid, etc., then just write no reaction. You can stop there. There's not going to be a reaction. However, if there is a state change into a gas, a liquid, or a solid, write out the correct formulas and balance the total equation. This is basically going to give you your molecular formula. Now, the next thing we want to do is we want to break up all those ionic compounds into their separate ions. So we always break them up into ions. We put a plus beside them, as we saw before. The key thing here is that the subscripts turn into coefficients. Because remember, what does this subscript mean? Well, it means that we have 3 Cl atoms. Like, for example, if I put a coefficient here, that means I had 1 times 2 and 2 times 3. I have 6 chlorine or chloride atoms, or ions, excuse me. So the subscript really turns into the coefficient here. Now, if you balance this as well, so for example, if you had 2AlCl3 and you broke that up into ions, so you'd have Al3 plus and you have Cl minus and you have 3 of those, well, that 3 also gets multiplied by the subscript from the balancing. So that means you'd have 2 of these and this would turn into 6. 2 times 3 is 6. So once we do that, once we split everything up into the ions, and remember it's just the aqueous compounds that are being split up. Anything that's gas, liquid, or solid does not get split up. It's just written as is. Identify the spectator ions, cross them out, and rewrite everything, giving the lowest whole number ratios to the coefficients. And when you've done that, you have now created the net ionic equation. So let's take a look at here. What happens when you react aqueous silver nitrate and aqueous sodium chloride? So our word equation here is very simple. It's pretty much there. It is silver nitrate plus sodium chloride. All right. Well, this is a double displacement reaction. So I'm just going to move my metals around. I'm going to form silver chloride. And I'm going to form sodium nitrate. Okay? So our molecular equation, so now what we're going to do is we're going to turn these into our molecular equations, so our formulas. So we have Ag and we have NO3. This is plus 1, this is minus 1, so we cross and we cross, and we get AgNO3, and that's aqueous. You can look at your solubility table to figure out if it's aqueous, but it also just says aqueous at the top there. Sodium chloride will be NaCl, again 1 plus, minus, cross, cross, and we get NaCl, again aqueous. Now what is formed? Well, we get silver chloride and sodium nitrate. So silver chloride is AgCl, this is 1 plus, minus, cross, cross, and we get AgCl. Now, when you look at this one and you look at your solubility table, we actually get this as a solid. And our final thing is sodium nitrate, Na and NO3. This is 1 plus and this is 1 minus, cross, cross. And we get NaNO3. Once again, because this is a nitrate, we're gonna know that it's going to be soluble, so it's aqueous. Everything looks balanced, so this is our molecular formula. And what we do see is that this reaction actually does happen, this double displacement reaction, because we are forming a solid here. So that will precipitate out, and we're forming it from 2 aqueous compounds. We form a solid, that is our precipitate. So here's a little demonstration of what's happening. And I use these wonderful PowerPoint slides from an individual, just kind of modify them, the acknowledgements in the back. But they do a really nice job as to showing what's actually happening. So here we have 2 samples. We have our silver nitrates and we have our sodium chloride. And when we mix them together in a beaker in this case, what we start seeing is that because they're aqueous, they split up into their individual ions. So AgNO3 split up into Ag plus, NO3 minus, and then the sodium chloride split up into Na plus and CO minus. So you can see that they're going to be kind of moving around in the solution. So our molecular equation was here, and we saw that once we put it into the water, they split up into their ions. So we're going to split these soluble solutions, so the ones that are aqueous, into their ionic forms. So Ag had a charge of plus 1, and again this is aqueous, plus NO3 minus, and this was aqueous. Now plus Na plus aqueous, plus Cl minus aqueous. All right, now we also saw that sodium nitrate, because it's aqueous, was also split up into its ionic form. So we have Na plus aqueous plus NO3 minus aqueous. Now we see that AgCl is a solid, so that means it's not soluble. It's not going to break up into its ions, so we leave it as AgCl solid. Okay, so that is now our total ionic equation. It's showing all the ions in the proper amounts. Everything is balanced, and we all have coefficients of 1 here, so this one's pretty simple. But we see that everything is in their ionic forms, except for the insoluble silver chloride. So once we see this kind of moving around, what we'll start seeing is that we should see a reaction between silver and chlorine to form that solid silver chloride, the insoluble silver chloride. So what we see is that as they get closer, there's going to be a reaction and we're going to form a precipitate. So that is the formation of our precipitate. We had an Ag plus ion react with a chloride ion, the Cl minus, and that precipitated out of solution. So this new compound was not soluble in water, and so that's why it formed a solid. It formed that precipitate. As you can see, the sodium ion and the nitrate ion, they keep moving around, and you know what, they might bump into one another and kind of attract one another, but they're not really going to form anything that's going to be precipitating out or, in a sense, turning into a gas. They're going to remain as aqueous. They're going to remain as ions within the solution. And so what you're going to see is because they remain as ions, as silver nitrate, there's not going to be any reaction. They remain as aqueous. There's no state change. And so what we're going to call them is we're going to call these things spectator ions. They don't participate in the formation of AgCl solid. They're just kind of there, other people in the swimming pool, but really this is what the reaction and the focus is all about. The formation of this AgCl, which is no longer soluble, it's insoluble, and so it forms a solid precipitate. So as we can see from this equation, this is our total ionic equation of the reaction that we've been seeing, we see that we have sodium and nitrate ion on both sides. Okay, they don't change their format. Ag went from aqueous and Cl minus went from aqueous to AgCl, that was a solid. So what we're going to do is we can actually highlight these. These are our spectator ions. So our spectator ions in this case is Na plus aqueous and NO3 minus aqueous. So if we cross these out, what are we left with? What we're left with is Ag plus aqueous plus Cl minus aqueous, because it's still, if you look at it, they're still adding to one another. And that's going to form AgCl solid. And that's it. So here's a second example. Here we have calcium chloride reacts with sodium nitrate. So the first thing to do is form our molecular equation. And so I'm not going to go through all the whole process. You should be able to know how to do this so far. So we're going to get CaCl2, and that's going to be aqueous, plus sodium nitrate, NaNO3 aqueous. And that reacts to form, so it's a double displacement. This is going to form CaNO3 2, and if again you look at the solubility table, it's going to be aqueous, plus NaCl, and that is going to be aqueous. We just need to balance. We have 2 there, we have 2 there, and now we're balanced. So when it comes to our total ionic equation, we're going to split up all these compounds, because what we see is they're all aqueous, 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 and aqueous. So when we do that, we get Ca2 plus, and I'm going to leave out the aqueous states here just for the sake of space. Now here, plus, I see that I have 2 Cl's, so that subscript is going to turn into my coefficient, 2 Cl minus. Again, that would be aqueous. Now here in the second one, we have a subscript in the beginning. So that not only multiplies the sodium, but it also multiplies the nitrate. So I have 2 Na positive ions, again aqueous, plus 2 NO3 minus, again aqueous ions. So I would be writing aqueous for all of these. This would be aqueous. I'm just trying to save some space here, and it's not really all that legible either. Now, moving on to the product side, I only have 1 calcium atom, so that's going to be Ca2 plus. Again, that's going to be aqueous, plus. Now, again, I have a subscript. I have a subscript right beside that NO3, so that means I have 2 NO3s. So I have 2 NO3 minus. And again, I have a coefficient already in the front because of my balancing my law of conservation of mass. That's going to multiply my Na and my Cl. So I'll have 2 Na plus 2 Cl minus. And once again, these are all aqueous. Okay. Now, what we're seeing here is something very interesting. If you just take a moment and look at both sides, our calcium has become an ion, our chlorides have become an ion, our sodium have become an ion, and our nitrates became ions. On the right side, calcium, nitrate, sodium, and chloride all became ions. And what you also notice is that we have two sodium atoms, two chlorides, two nitrates, one calcium. They're in identical formats. So what we can see is, really, is there any state change here? And the answer is no. There's no state change. So if we're going to go ahead and cross out all the things that we see on one side, well, I see calcium here in 1, 1. I have two chlorides, I have two chlorides. I have two sodiums, I have two sodiums. I have two nitrates. I've crossed everything out. Technically, everything, all of them, are spectator ions. So what is our net ionic equation? We don't have one. Because what we see is that our products are both aqueous. There is no reaction that has occurred in this situation. So this is why when we say that when we have our products that are aqueous, the reaction doesn't happen. Well, because they don't. There's no state change. There's no new substance being formed. It's just the same as we had in our reactants. So for these equations, what I would like you to do is develop the molecular, the total, and the net ionic equation for these sentences here. Also, while you're doing that, please identify the spectator ions and box up your final net ionic equation. So, pause the video, take as much time as you need. Once you're done, press unpause, and we'll have the answers for you. All right, go ahead and pause the video. All right, welcome back. So here what we see is that we had two spectator ions. We had Na and we had chloride, and that gave us, it's going to change here. So that gave us, left us with Ba2+, and it also left us with our sulfate ion. And so what we had is we had a state change. We had BaSO4 solid. So our net ionic equation was Ba2+, aqueous, plus sulfate aqueous gives us BaSO4 solid. So this reaction did happen because we did form a new product with new properties that was insoluble in water, while the original reactants were soluble in water. The second one here we had was a little bit interesting, was a single displacement reaction. So aluminum was a solid, and we also produced hydrogen gas. We did produce two compounds here as per a single displacement reaction. And so what we do is, because this is a solid, we just write it as is. Because this is a gas, we write it as is. And what we did is we saw that there was a breakdown. Now this was an interesting one because we have subscripts and coefficients, so they multiply together to create 6 hydrogens. And 3 is in front of the SO4 as well, so we have 3 of those. And what we saw was that we had the SO4s on both sides, again, 3 and 3. And that's an important point. You really have to make sure that you have the same amount on both sides, 3 and 3. So our spectator ion in this case was just one of them, SO4 2-, and our single displacement reaction was all about 2 aluminum atoms reacting with 6 hydrogen, or as we call them, protons, hydrogen ions, 2 aluminum ions, and forming 3 hydrogen gas molecules. So once again, pause the video, come up with a molecular, total, and net ionic equation, identify any spectator ions, and we'll be back with the answers as soon as you're finished. So go ahead, pause the video now. Alright, so welcome back. The first one was actually a little bit easy because all of the reactants were in a format that was not aqueous, so they weren't able to be dissolved in water. We had gas, liquid, and gas. So they are just written right as is. Here we had the formation of nitric acid, and so this is aqueous, so it could be split up into its H+ and its nitrate ion. And what we can see is that, well, these ones don't really have the same thing on this side. So there are no spectator ions. We don't have anything on the left side that we also see on the right side. No spectator ions. So in this case, the total ionic equation and the net ionic equation were the exact same. In the second one here, what we can see is that we have a double displacement reaction. And if you remember, here, aqueous and aqueous, we have no reaction. Now, if you're saying, wait a second, sir, I remember that something about H2SO4. Well, remember, it was actually H2SO3 aqueous that breaks up into H2O liquid and SO2 gas. So be careful about that. It's only that unstable sulfurous acid. So here we have sulfuric acid, which remains aqueous, and we have our iron 3 chloride, again aqueous. So if we were to do our whole our total ionic equation, we'd see that everything would be aqueous, all of them are spectator ions, and there would be no reaction. So if you figure that out right away, you could have just put NR over here, and then this would be nothing, 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 nothing. So that's pretty much it. So thanks very much for watching. Hopefully we'll see you next time. Have a great day.